Alrighty, folks. So today we'll be talking about section 4.7, which puts us in the home stretch of the class. We've got one more week's worth of these left to go. And this is all about applied optimization, which is a fancy way of saying, you know, all that extrema stuff we've been doing? Well, now we're going to do it for word problems. So most of the section is examples and a description of the process, like we had for related rates. Right, so the first is, again, similar to the related rates, we're going to ID the variables involved, set something aside for them. 2, we need to ID the function we want to optimize and the interval. So usually in these problems, we're looking for either an absolute maximum or an absolute minimum. And in order to be sure we have one of those, if you recall from our section on extrema, that means that we need to have a closed and bounded interval. Now, sometimes we're not going to have a bounded interval, like we're going to do in our first problem here. But that just means we have to check one little extra thing to make sure that extrema exists. And then lastly, we want to find the extrema. And if we find the right extrema, that's going to be the optimal value for that function. So we're going to hop right into problems. So the first one's going to be a nice, quick one that I can write by hand. The rest of them I have squared away at the bottom of the canvas, some word problems, so I don't have to write all that out for us. So the first one is find two positive numbers whose product is 50, where 2x plus 2y is as small as possible. Okay. So as we're looking at this here, with our first step, we want to ID the variables. Now in this case, they've already sort of been given to us, right? So two positive numbers, x and y, right? So these are our variables. Now, the function we want to optimize is clued in by this phrase right here, right? As small as possible means we're looking for a minimum. So the function we want to optimize is the thing we want to make as small as possible. So it's 2x plus 2y. So we have a little bit of a problem here, which is that we're in Calc 1. We don't have multiple variables in our functions that we're taking the derivatives of. So we need to see if we have enough information to turn this thing we want to optimize into a function of one variable. And thankfully we do, right? This piece right here says we also know that x times y equals 50, right? And so let's say we want to make it f of x because we're used to doing x. That means that we need to figure out a way to replace this y. And it turns out we can replace the y that way, right? So that means that f of x is actually 2x plus 2y, but with x's instead. And so we can simplify that to 2x, plus 100 divided by x, right? So this here is the function we want to minimize. And we also know that we're looking at positive numbers, so that's the bit that's going to tell us the interval, right? So we found the function we want to optimize. Now we need to find the interval, and the interval needs to describe what x is allowed to be, right? So in this problem, the interval is 0 to infinity, right? Now, this is not a closed or bounded interval, so we're going to have to do some stuff to figure out what's going on here, right? But that comes at the very end. Now we're at the point where we need to find the extrema, right? So if we recall back from that section, that means finding the crit points, which means we need to find our derivative. Right? We could also think of this as 2 to the x plus 100 times x to the negative 1. So the derivative of these power functions, this is linear, so we just take the coefficient. For this one, we bring the negative 1 down, and we subtract 1 here, so it becomes negative 100 times x to the negative 2. Right? Or in other words... Right, and looking at it like this, we know that it does not exist clearly when x equals 0, right? Because the only possible problem could be that the denominator of the fraction is 0. And the other thing we want is when is it equal to 0? Right, this is going to be when 2 is equal to 100x squared, which happens when x squared equals 50. So x is going to be plus or minus the square root of 50. Now, we're looking at a very particular interval here. So this is not a valid critical point because it's not in our interval. And neither is the negative version. So our critical point is just going to be positive square root of 50 for this problem because that's the only one of our critical points that lies in our interval, right? So, usually, if we have an interval AB, we're going to be checking the endpoints and the critical points, right? If we recall that from our extrema. Now, we can't do that in this case, so instead of checking those endpoints, we're going to check the limit as x approaches 0 of f of x. We're going to check the limit as x approaches infinity of f of x. And we're going to check f of the square root of 50. Right. So the limit of f of x as x approaches 0 is 0 plus infinity. As much as that makes me cringe, but that's just infinity. And similarly, we get infinity over here. Right? So... what that means, what these limit means, the fact that they go to positive infinity tells us that we cannot have a maximum of this function, right? We said before that anytime we're looking at a closed and bounded interval, we always have an absolute max and an absolute min, right? But the fact that our interval is not closed and bounded, in this case, means that we don't have an absolute maximum, right? Because the limit as we approach our ends is positive infinity, right? That means that no matter how big we can always get bigger by either choosing closer to 0 or closer to infinity, and therefore we cannot come up with a maximum. Thankfully, this problem doesn't care about a maximum. This problem wants a minimum. Right, so we're going to presume that we get it at f of 50, square root of 50 rather, which is 2 root 50 plus 2 100 divided by the square root of 50, which is 2 root 50 plus 2 root 50, so we get 4 root 50. So that is the maximum of that function, or minimum rather. So 2x plus 2y, the smallest it can be is 4 root 50. But that's not what the question asked. It asked for an x and a y, right? So this is at x equals root 50. And y, we know, is equal to 50 divided by x, which is root 50, right? So whenever we do this step, this step of substituting in, if the problem asks for all of the original variables, we have to plug them back out. If it just asks for the maximum or minimum, it's going to be whatever we plug into the function, and that's fine, right? But if it asks for the numbers that make it 50, right? So in this case, the question is asking for what is x and what is y, then we're going to have to take the one variable we get and plug it in for the other, unsubstituting it in a way. All right. Let's see. Let's do another problem. Let me take a trip down to the bottom of the canvas and pull one of these guys up. There we go. Alrighty. So the monthly output of a certain light bulb factory is P equals 2LK squared in millions, where L is the cost of labor and K is the cost of equipment in millions. Company needs to produce 1.7 million units per month. Which values of L and K would minimize the total cost L plus K? Right? So for this one, IDing our variables is pretty easy. We've got L and we've got K. And minimizing our function is, or the identifying the function that we want to find the extreme of, is here, right? So it wants to minimize the total cost. So we saw above, we said as small as possible. Minimize is, of course, another way of saying that. So that's going to be the function that we want to minimize. But again, we can't do our process if we have two variables, right? So we also know that 2LK squared equals P, and we know that we want P to be 1.7, right? So last time it just sort of gave us those constraints, the fact that the two numbers had to multiply to give 50. In this case, we've got to kind of build it together that we know what the production is, we know what the output is, and later it tells us what number we want that to be, right? So I think I don't want to take the square root of anything, so I'm going to solve for L. That's 1.7 divided by 2K squared. So I know that f of K equals 1.7 divided by 2k squared plus k. Right? Now, in this case, we need to find the interval again. And similarly, we might not have a closed and bounded interval, but we'll have to do the same sort of thing as we did before, right? And looking at it, we can see that cost of labor and cost of equipment, it doesn't say that they're positive, but in the context of the problem, it doesn't make sense for them to be negative, right? The cost of labor and the cost of equipment is never going to be negative, right? Nobody's going to, it's not reasonable to expect someone to pay the factory explicitly for the ability to work there and not get paid themselves, right? And even less for equipment. So we know that the interval that we're looking at least in terms of the context of the problem, is 0 to infinity including 0. But we look at the function and we can see that really it should be this again, right? Because we can't plug in 0 to that function, right? 0 is not in the domain of that f, so we need to not include it as the interval that we're looking at. Right. So now we need to find the extrema. So we need to find f prime of k. Again, this is 1.7 over 2 k to the negative 2 plus k. So it's going to be negative 2 times 1.7 over 2 k to the negative 3 using our power rule. And that linear term, we're just going to get the coefficient out of it. If I simplify this, this is negative 1.7 divided by k cubed plus 1. And so by inspection, we can see that it's again going to not exist at k equals 0. But that's not going to be one that we care about because that's not in our interval. Right, so we also need f prime of k equaling 0. So we need the function to equal 0. That's the same thing as 1 equaling 1.7 over k cubed, which is the same thing as k cubed equaling 1.7. So k equals the cube root of 1.7. Right, now, I don't have to plug that into a calculator to know that that's positive because the cube root of a positive number is always positive. So I know that this guy is a critical point that I need to look at. So my critical point is the cube root of 1.7. All right. So now we need to plug in, and again, we don't have endpoints, so we have to do it by limits. But, spoiler, we're going to get a very similar looking thing. I mostly wanted to do this one to look at how different problems are phrased. So if we go to 0 here, if we look at our power rules, that's going to be infinity plus 0. So we get infinity. Again, if we look at how our limits work for power functions, this is going to be infinity as well. So again, that tells us that we're not going to be able to find a maximum of this function, but that's okay because we wanted to find a minimum. Right, so our minimum, we know it's going to come here because this is the only possible point it could come. So this is going to be 1.7 2 times the cube root of 1.7 squared plus the cube root of 1.7. So this is 1/2 times the cube root of 1.7 plus the cube root of 1.7. I don't know where a 5 came in there. So this is going to be 3/2 cube root of 1.7 is going to be the minimum total cost, right? But again, it didn't ask what the minimum total cost was. It asked what values of L and K would minimize the total cost, right? So we know that the K that minimizes it is the cube root of 1.7, and the L that minimizes it is going to be 1.7 times 2 over the cube root of 1.7, which is just 1/2 the cube root of 1.7. Right? So our final answer is going to be this K and this L value, because that's what was asked for. What values of L and K would minimize, it's kind of hard to read when I do that, but what values of L and K will minimize the total cost? What not, right? This would be the answer if the question was, what is the minimal total cost, right? So that's just something to pay attention to in the wording of these problems. I'll go grab another one. I'll grab some white space too. All right. So this one is asking us to find points on the line y equals x minus 1, closest and farthest. So this one is looking for a minimum and a maximum to the point 0, 0, right? So first off, right, we are gonna look for a point. So the variable is going to be a point xy. Right, so a point on R2. And the function that we want to minimize, that one's a little bit tricky and requires us to remember a rule about geometry, right, or a formula from geometry. Closest and farthest means the smallest distance and the largest distance, right? So really when we're looking for optimization problems, we need to be looking for something that means the smallest and the biggest, right? And what they're the smallest and the biggest of is the thing we want to be optimizing. So closest and farthest is the smallest and biggest of the distance function, right? So we need to remember that the distance between xy and AB is the square root of x minus a squared plus y minus b squared. Now, that's not too bad of a function, but it turns out that if x squared, let's not use x, m squared is less than n squared, then m is less than n. So what this means is that anytime we want to minimize or maximize distance, we can also minimize the square of the distance. So we're going to use, we're going to minimize x minus a squared plus y minus b squared, right? And to make our lives even better, this is the AB in question, right? So for us, this is x minus 0 squared plus y minus 0 squared, or in other words, x squared plus y squared. Great. That looks way better than what we started at. I don't know about you, but it looks way better to me. So we're going to try to minimize this, right? Again, we have a little bit of a problem, which is that there is two variables there, and we can't take the derivative of something with two variables yet. So we need to find our constraint. And that's going to be that this point that we care about is on the line y equals x minus 1, right? So because of that, we know that, well, y equals x minus 1, right? So that means that f of x is going to be x squared plus x minus 1 squared. Right, maybe we want to simplify that a little bit. X squared plus x squared minus 2x plus 1. So we get 2x squared minus 2x plus 1. Yeah, that seems good to me. Right, so now we want to go ahead and find the extrema. Right, so that means taking the derivative. And this is just a whole bunch of power functions, so it's not too bad. Right? There's nowhere that this doesn't exist. And f prime of x equals 0 means that 2 equals 4x means that x equals 1/2. Right? So that is our only possible one, which means, right, just looking at this right off the bat, well, okay, first off, it means that I skipped a step, right? We're supposed to find an interval. But if we look at the line y equals x, x itself is allowed to be anything on that line, right? That line is, right, this guy. X is allowed to be anything it wants, right? So our interval is going to be this guy, not closed and bounded at all, right? So we need to take the limit as x goes to negative infinity of f of x. We also need to find the limit as x goes to infinity of f of x. And we need to find f of 1/2. Right? So, this guy, remember for polynomials, you really only have to check the leading term. So this is going to be the limit as the same as the limit as x goes to negative infinity of 2x squared, which is infinity. And this is going to be the same as the limit as x goes to infinity of 2x squared, which is also infinity. So what this tells us is, again, I accidentally picked examples that all go to positive infinity, that there is no maximum, right? Thankfully, our problem specified should they exist, so the furthest does not exist, right? And so we might as well check this guy. This is going to be 2 times 1/2 squared minus 2 times 1/2 plus 1. This is 1/2 minus 1 plus 1. Well, hey, 1/2 again, right? So, all that really did, we just wanted that not to be negative infinity somehow. Because otherwise that's our only possibility for being the minimum. And as long as none of the things in question go to infinity, negative infinity, then we are going to have a minimum, right? So that's one of the things, all these problems, went to negative infinity, or went to positive infinity rather, if any of them had gone to negative infinity, that would tell us that there's not a minimum, right? We can keep going down as negative as we want to go. There's no smallest number. So the point that we care about is going to have x equaling 1/2. Y is going to equal 1/2 minus 1, so negative 1/2. So the point that we care about is 1/2, comma, negative 1/2. That should be what our final answer is, because it said find the point. So we don't have time for that, or we don't have space for that last problem, rather. But, you know, you can try it out to practice. I'll go ahead and leave it on the page. And next up, we're going to talk about a way to approximate things. So it's going to be one where we're going to heavily rely on technology. I'm going to bring up a new app, a specific kind of calculator. Not really kind of calculator, but we'll see then, and I'll see you next time.